All right, welcome. Today we are jumping right into Chapter 3 of An Introduction to Parallel Programming. We're going to talk about how you get a whole bunch of separate computers to work together on one single massive problem. And the secret sauce to making that happen is something called the Message Passing Interface, or MPI. So let's dive in. So here's the big question, right? This is what drives everything in supercomputing. When one machine just isn't going to cut it, you need an army of them. But how do you actually command that army? You need a system, a language for them to coordinate, to share info. And that system, well, that's exactly what we're here to talk about. To really get a grip on this, you have to understand the two basic ways this can be set up. First, you've got shared memory. This is the giant whiteboard model. All the processors, the workers, they all share one big memory space. Seems easy, right? But what we're focusing on today is the other model, distributed memory. This is the private notepad model. Each processor has its own little world, its own memory. They're totally separate. The only way they can cooperate is by literally passing notes back and forth, sending and receiving messages. Okay, so here's our game plan for today. We're going to start with the basics. What even is MPI? Then we'll look at the essential commands, your first baby steps in an MPI program. After that, we'll use those ideas to solve a real math problem. We'll even look at smarter ways for our computer team to talk to each other. And finally, we'll answer the big one. Was all this effort actually worth it? Did it make things faster? First up, what is MPI? Well, think of it as the official rulebook for passing those notes between computers. And here's the key thing. It's not some brand new programming language you have to learn from the ground up. Nope, it's actually a library, just a set of tools you can use in languages you probably already know, like C. And here's the more, textbook definition. It's a specification. It's the blueprint, the standard that everyone agrees on for how these processes are going to talk to each other. This is the industry standard for programming those huge supercomputers that are out there, solving some of the world's most massive computational challenges. All right, enough theory. Let's get our hands dirty and see how this actually works. We're going to look at just a handful of commands that are the absolute backbone of pretty much any MPI program you'll ever see. This is like learning to say hello world in the language of parallel computing. So, every single MPI program has to have a clear beginning and a clear end. MPI in it is like firing the starting pistol. It tells all the processes, okay, meeting started, get ready to communicate. And MPI finalized is the cleanup. It shuts everything down nicely. Anything you want to do with MPI, it has to happen between these two function calls. It's that simple. Now, once the meeting started, you need a little organization. MPI comm size basically does a head count. It answers the question, how many of us are on the team today? Then you have MPI comm rank, which gives every single process a unique name tag, an ID number that starts from 0. And this right here is absolutely critical. I mean, without a unique rank, how could you possibly tell one process to do one job and another process to do something totally different? You couldn't. And this is the whole ballgame. This is the actual passing of the notes. MPI send does exactly what you think. It bundles up some data and boom, sends it to another process using its rank. On the other side, a process that's expecting that message calls MPI receive, and it just sits there waiting until that note arrives. This little dance, this send and receive, is the fundamental building block of everything we're doing. So let's see how these pieces actually snap together. In a super simple greetings program, we can have a manager, let's say process 0. And all the other processes, ranks 1 and up, they all use MPI send to fire off a little hello message to the manager. Process 0 then just sits in a loop using MPI receive over and over to collect all those greetings, and then it prints them out. It's a simple idea, but it shows you the core mechanics perfectly. Okay, sending hello messages is cute, but it's not going to cure any diseases. Let's solve a real problem. We're going to use something called the Trapezoidal Rule, which is a classic way to find the area under a curve. And it's a perfect example for us because you can easily chop the problem up into a bunch of smaller, independent pieces. So the game plan here is a classic divide and conquer. Process 0 is our manager. It figures out the whole problem and then hands out a small slice of the curve to every single worker process. Each of those workers then goes off on its own and calculates the area for just its little piece. Once they're done, they send their answer back to the manager, who adds it all up to get the final result. This manager-worker setup is a super common and powerful pattern. So it worked. We got the right answer. But was it smart? Having one single process collect every single result one by one, that creates a massive bottleneck. We can do way better. Let's look at how to make these processes talk more like a real team. I mean, really think about this for a second. If you have 1,000 processes, or 10,000, process 0 is going to be sitting there for ages just waiting to receive thousands of individual messages while all the other processes are finished and just twiddling their thumbs. That doesn't really feel very parallel, does it? There has to be a smarter way to add up all those results. This really shows the difference. On one side, you have our first approach, point to point. Every worker reports to the boss, and the boss gets totally buried in messages. But on the other side, you have collective communication. Instead of everyone yelling at the manager, processes pair up and add their results. Then those pairs team up, and so on and so on. It's this beautiful, efficient tree structure that shares the work of adding everything up. It is so much faster. And you know what's awesome? MPI already has the perfect tool for this. It's called MPI Reduce. You just tell it, hey, everyone has a number, I want you to add them all up and give the final answer to process 0. And MPI takes care of all that complicated, tree-structured communication behind the scenes for you. It's clean, it's powerful, and it is a massive performance boost. All right, we did all this extra work. We made our code a little more complex, hopefully a lot more clever, but was it worth it? This is the moment of truth. Let's look at the actual numbers, because the whole point of this is to go faster. We need to measure it. Okay, check this out. This table shows us the speedup. That's how many times faster our parallel program is than the original. Now look at that top row. For a small problem, yeah, we get a little faster, but the gains kind of level off. But now look at the bottom row. For a much bigger problem, with 16 processes, we are running 15.5 times faster. That is almost perfect speedup. This tells us something incredibly important. And what we're seeing here has a name. It's called scalability. Specifically, this is weak scalability. All that means is that if you want to keep getting great performance as you add more and more computers, you also have to give them a bigger problem to chew on. And that is fantastic news, because the whole reason we're doing this in the first place is to solve those gigantic problems that would never fit on one machine to begin with. So there you have it. We've seen how to take a bunch of independent computers, organize them into a team, give them their jobs, and have them work together to get a result way faster than any single one could. These tools, the tools in MPI, let us tackle problems that are just on another level. So the only question left is, what are you going to build with it?